Hi, this is the first of a series of videos going over the midterm on chapters 3 and 4. So I'm going to just kind of work my way through. The first question asks if data from the same sample are used to make a 90% confidence interval and to make a 95% confidence interval, how will the confidence intervals compare? Remember, just if I want to be more confident, my confidence interval, the idea is that I'm trying to create an interval that I'm confident will capture the true but unknown value of the population parameter. And so if I want to be more confident, I need a wider range of values. And if I don't mind being less confident, I can include a narrower range of values. So the 95% confidence interval should be wider than the 90% confidence interval. The answer there is A. Because they are using the same sample data, though, they would be centered around the same value because, remember, the sample statistic is what determines where the center of the confidence interval will be. Question 2 says, what is the name given to a distribution of statistics that are calculated from many different samples of the same size, selected randomly from the same population? This is the definition of a sampling distribution. Remember, to be a bootstrap distribution, instead of selecting randomly from the same population, I'd be selecting randomly from the original sample. If a randomization distribution would be simulating samples, assuming that the null hypothesis is true. That's not the case here. In a significance distribution, that's just something I made up because I couldn't think of anything else it could possibly be, and I needed a fourth answer. Journals are more likely to accept articles describing results that are statistically significant than results that are not. The name for this phenomenon is publication bias. Those that are statistically significant results are more likely to be published, and so we're more likely to hear about them. Question 4. Which of the following significance levels will require the strongest evidence to reject the null hypothesis? Remember that we reject the null hypothesis when the p-value is less than our significance level, which we call alpha. And so the smaller this significance level alpha is, the smaller the p-value, the stronger the evidence needs to be to reject. So the one that would require the strongest evidence would be the one that's the smallest, D. Question 5, we are told that the distribution of prices among all 1-carat diamonds sold in the United States has a mean of $4,250 and a standard deviation of $625. If a random sample of 100 1-carat diamond rings is used to estimate the mean price among all 1-carat diamond rings sold in the United States, the standard error of the sample mean is $62.50. So question 5 asks, if I use 2 different random samples are selected from the population of all 1-carat diamonds sold in the United States, one of them is a sample size of 100, the other is a sample of size 30, which one would be more likely to result in a mean price between $4,000 and $4,500? So whenever you see a question that is looking at whether a particular sample result would be more likely or less likely with 2 different sample sizes, these are always questions about how sample size affects the amount of variability in the sampling distribution. So I think it's always easiest to sketch. So let's suppose for a minute I'm looking at samples of size 100. I know that if I'm taking random samples, the distribution of sample statistics, the sampling distribution that I would get from many different samples, is going to be centered around the true population parameter. In this case, that's the population mean of $4,250. I also know that unless the sample is extremely small, it's going to be a bell-shaped distribution of statistics, so something kind of like this. And I wouldn't necessarily normally know how much spread there would be, but I do know here that the standard error is $62.50, so I could sort of get a sense of exactly how that is, but I don't really need to, because I know that if this is my distribution for a sample size of 100, if I were to use a smaller sample size, the standard error would be larger. Remember, when I have a bigger sample, I get a more precise estimate of the true population mean, and so I get less spread in my sampling distribution. So with a smaller sample size, my distribution is still going to be approximately bell-shaped, and it's still going to be centered in the same place, but it's going to have more spread. So say for n equals 30, my distribution might look more like this. Now I can think about, okay, what's the range I'm interested in? I'm looking between, let's see, between 4,000 and 4,500, so that's 4,250 is right in the middle of that range. And now I can look and see, okay, which of these distributions has a larger percentage of it inside? That's the one that's going to be more likely to give me a mean that's in that range. The one that has more of the distribution of the sample statistics outside of that is going to be more likely to give me something that's farther away. So here we can see that since there's more of the distribution is inside between 4,000 and 500 when we're using a bigger sample size, the correct answer there is A. So again, whenever we're answering questions and we're comparing two sample sizes and looking for a sample statistic, would it be more or less likely? Always try to remember it's a question about variability in the sampling distribution, and it's usually helpful to draw a picture. Questions 6 and 7 also relate to the same scenario. Here it's looking at the distribution of prices among all 1-carat diamonds sold in the United States. Again, it has a mean of $4,250 and a standard deviation of 625. So that tells me about the distribution of diamond prices in the population. And that's of individual diamonds. So it's centered around 4,250. Has a mean of $625. So if I quickly go 1 and 2 standard deviations above and below that, 4,250 plus 650 brings me up to 4,900. Plus another 650 would bring me up to 5,550. If I go down 2 standard deviations from there, I think I added 550 instead of 650 instead of 625. Darn it. Should be a 75. This should be a 00. There we go. Alright, sorry about that. Okay, so let's go down by the same amount. So down by 625 gives me down to 3,625, and down another 625 brings me down to 3,000. So I've got some sort of distribution that looks like this. It might not be exactly bell-shaped, but just for a rough idea, get something that looks like this. Now, I also know that the standard error is 6,250. So if I were to look at the sampling distribution, remember sampling distribution is centered around the true population mean. What it shows me is how sample means would vary for random samples of n equals 100. And so now I say, okay, well now my standard error is only 6250. So if I say, okay, 4,250 plus 6250, one standard error above that is only $4,312.50. Two standard errors, you get the idea. I get a much narrower distribution here. So here's my sampling distribution. Right. Now what I'm trying to decide here is whether it would be surprising to take a random sample and find a mean of 4,500. So if I look in this distribution, you can see one standard error is 4,312.50. If I go up one more standard error, that's second one here is at 4,312.50. Right? So 4,500 is more than two standard errors up in the sampling distribution. It's somewhere out here. Right? The key is to recognize that because the sampling distribution and the standard error tells us what's typical in a sample mean, right? Typical amount that a sample mean will differ from the population mean. This is many standard errors away from the true population mean, that would be an unusual sample. It wouldn't be an unusual individual diamond, but it would be unusual to see a sample of 100 diamonds with a price that's that high. So when we're thinking about an unusual mean, we just have to recognize that we're using the standard error as a measure of what's typical and what's not. So the answer here should be, let's see, yes, because a mean of $4,500 would be more than two standard errors away from the population mean. And the last question about this scenario asks if we were to take two different samples, one of 100 diamonds and one of 30 diamonds, which would I expect to yield a wider confidence interval? This comes back to the fact that when we have a larger sample size, we tend to have less variation in the sample statistics, tend to get closer to the true value of the parameter that we're trying to estimate. So we have a smaller standard error, and since the margin of error for our confidence interval is 2 times the standard error, it also means we make a narrower confidence interval. So which would I expect to have a wider confidence interval? Well, the larger one would give the narrower confidence interval, so the one with the wider one should be the smaller one. So we'll stop there and pick up with the next video for the next question.